In this video, we'll apply the concepts learned in the previous unit to a practical problem. Consider flow through a pipe with a constant mass flow rate of air of 10 kilograms per second at an inlet stagnation temperature of 400 Kelvin. We intend to burn butane with the molecular formula C4H10 in this pipe. We are asked to calculate both the air-fuel mass and molar ratios for butane air combustion. In addition, we are also asked to compute stagnation temperature at the exit and heat added per unit mass of flow if the equivalence ratio is given to be 0.9. And LHV of butane for combustion is given to be 49.5 megajoules per kilogram. Recall that the heat added per unit mass of flow is an important quantity and is used in our formulation of flow with heat addition. We are also given the molecular weights of air and butane, combustion efficiency of 95%, Cp of air, and we are told to not neglect the mass flow rate of fuel. Let's proceed with the solution. The first thing to do is to write the balanced chemical reaction for butane air combustion. We have learned how to do this in the previous unit. Therefore, let us apply that knowledge. We know that the number of moles of oxygen, A, required to fully react all of the fuel is given by X plus Y over 4. Corresponding to this, the molar and mass-based stoichiometric air-fuel ratios can be calculated by these two expressions. Substituting X equals 4 and Y equals 10 for butane into the expression for A and evaluating all other ratios, we get A equals 6.5, the molar ratio at stoichiometry N equals 30.94, and the mass air-fuel ratio at stoichiometry M is 15.42. Next, we are asked to calculate the stagnation temperature at the exit. In order to calculate this, we need to enforce an energy balance. That is, the actual heat released due to combustion should equal the change in total enthalpy of the flow. To evaluate actual heat released, we need to use information given regarding the equivalence ratio and the combustion efficiency. Since equivalence ratio is 0.9, the mass-based air-fuel ratio M will be different from that at stoichiometric proportion and is given by M equals M at stoichiometry divided by the equivalence ratio phi, as we have learned before. This comes out to be 17.13. Once M is known, we can also calculate the fuel flow rate as given by this expression here as M dot fuel equals M dot air divided by M. Therefore, we can write the actual heat released that accounts for inefficiencies in the combustion process as the product of combustion efficiency times mass flow rate of fuel times the lower heating value. This should equal the change in flow enthalpy given as total mass flow rate multiplied by Cp times the change in stagnation temperature from the inlet to the exit. We can cancel the M dot air as it occurs on both sides and rearrange terms to write T naught or the stagnation temperature of the exit as given over here. This evaluates to a value of 2980.92 Kelvin once we substitute values for all the variables. Finally, we are also asked to compute heat added per unit mass of flow, as might be required in a real scramjet engine. This can be calculated as the ratio of actual heat released to the total mass flow rate, which comes out to be 2.59 megajoules per kilograms, again substituting values for each of these variables. The same procedure can be used for other fuels at different equivalent ratios to evaluate the total heat added per unit mass of flow. You will be expected to do some of this in the assessment, both for the combustors portion as well as the overall project.